So good morning, everyone. So I sent you an email about these important dates in March. So we have different submissions here in March. The first phase of the project is going to be March 1st. Okay. If you go to the project description, you can see exactly what I need in this phase. Okay. Number two, quiz 2 is going to be on March 9th. Okay. Homework 1 is going to be March 18. Midterm is going to be 26. Okay. So anyway, I'm going to record. I already sent you emails about these dates, and this video is going to be recorded, and I'm going to post it. Okay. So what I did last time I was explaining digital transmission. Okay, digital transmission, and simply I told you, if your data is digital, so here you have to convert the digital data into digital signal to transmit your data. Okay, so you're not gonna convert your binary data into analog, okay, or analog to binary data. That's what we're gonna do in the next topic. But here in this topic, I'm going to transmit the data in digital signal, okay? And I already explained last time, and that's very important to know. If you have, that's why we need to use encoder and decoder. So here you have encoder, okay? And here we have decoder. Last time also I explained how can you tell if the encoder and decoder is good or bad. How can you tell that? So I explained last time. The first one is the signal rate. This signal rate, okay, or the signal rate or bandwidth. This is for the same bit rate, how much bandwidth you need from the network, right? So the small, little bit confusing. Please listen to me. What I'm saying is that for the same bit rate, for the same N, the smaller the bandwidth is the better. You got what I'm saying? The smaller the bandwidth is the better for sure. Because you are asking the network to give you smaller amount of bandwidth to transfer the data, which is good. Okay. So, and as I started to do last time, for every encoding scheme, you need to calculate R. And actually, R, the higher the R is the better. And you can see here, higher R means a smaller signal rate. Okay. Also, I talked last time about DC component baseline wandering. If your encoder is good, it should not have DC component. It should not have baseline wandering. It should have self-synchronization. Okay. So, and also last time I started to explain, or already explained, the first one is unipolar. For exams, for quizzes, what you should know here. The first thing you should know, given if I give you a binary pattern like this one, can you draw the signal, the voltage, how the signal looks like? So you should, and also the opposite. So this is the first thing you should learn for every encoder. Okay. Binary to signal, signal to binary. Okay, so this is number one. Number two, you should learn for every encoder what is the bandwidth for every encoder. Okay, what is the advantages and disadvantages? So you should know this encoder has this component or not. Okay, and why. Okay, and that's actually what I explained, and that's also what I'm going to continue explaining today as well. Okay. So the first one was very simple, non-return to zero, as I told you before. As the bandwidth was too good and so on, but it has for sure DC component and baseline wandering and so on. The second one was polar, and in case of polar, I explained the level and the inversion, and you can tell in case of level. So actually, you can tell if the bit is 0 or 1 actually from the voltage level. So the voltage level can tell you. But here for inversion, you can know if it is 1 or 0 from the inversion. If there is inversion or no inversion. Okay. This is where you can know. So the level is not going to tell you. What's going to tell you here is if there is inversion or not. Okay. And actually, as you see here, every time I calculate R, and then from R I calculate S. Okay. So for example, here R is equal, every time slot will transmit 1 bit in one time in one signal element, and so on. Okay. Yeah, for everyone I explained if it has DC component or not. Also, in case of return to 0, what you see here, what we did, every time we return to 0. So inside every bit rate, we have to return it to 0. We have to return it to 0. Okay. And I told you before, this is good for synchronization, because simply every time there is a transition here, the receiver can synchronize. Okay, can modify the clock to synchronize. That's what the worst thing for synchronization, if you have constant voltage this way, okay, either positive or negative or 0. The more transition you have, this is going to help the receiver to resynchronize. Okay, as I told you before. Okay, this is good, but this is good for synchronization. However, and this is a bad thing. The bad thing, R is small now. That's bad. Why? Because you are gonna transfer 1 bit. R is equal 1 divided by 2. I need 2 signal element here. 2 signal element. It's like you need 2 cars to transfer one passenger. Okay, or to transfer 1 bit, I need 2 signal elements, which is bad. That's why here you can see I need the double of the bandwidth comparing to what we had before. What we had before was N divided by 2. Yes, so by this transition, I fixed some problems, but bandwidth is so bad, as I explained before. Okay? And then by the end of the lecture last time, I started to explain Manchester and the differential Manchester. And you can see here in Manchester, you can see always for any bit rate, have positive, have negative, always. But if you start by positive and then negative, this is 0. If you start by negative and then positive, this is 1. But always half of the time positive, half negative, half positive, half negative, half positive, half negative. So, and always there is transition. Because always there is transition, this is good for synchronization. And because half positive, half negative, this is good for DC component. You got what I'm saying? So if you have a pattern like 1, 1, 1, 1, 1, so it's not going to be fixed voltage. It's going to be high, low, high, low. Same thing for 0, 0, 0. So it's really good. Okay. So here also differential Manchester here, similar to what we explained before. This is like level, non-return to 0 level, and this one is actually like inversion. So here, this is the same idea of inversion we used to before. You can tell if the bit is 1 or 0, if there is a transition or not. So here, for example, here we are positive. Let me point it here. Here we are positive and then remains positive. Okay? Keep in mind, still we have one transition in every bit duration. Is still half of the time positive, half the time negative. This is still right, but the difference is that here you are positive and still you are positive, no transition, so it is 1, right? Here, okay, it is negative and then negative, and after negative there is a transition here, negative and then positive. That's why this one is 0. So every time there is inversion or transition, so inversion, so it's 0. Same thing here, negative and then positive, so it is 0. Okay, negative and then negative, no transition, so this is 1, and so on. Any questions? Yeah, sure.
There's no inversion, and it's bit with 1, right?
Yes, 1 means no inversion, because there is no inversion. Yeah, this one here. Next one, not the previous one, next one, right? So here, this one, there is no transition. So the next, not the previous, next one is 1. You get what I'm saying? Same thing here, because this one is 0, so the next one is there is transition, so it's 0. Is that okay? So everything looks here okay. Everything looks okay. Synchronization is good. Baseline wandering is good, but still, the main problem here, you are using 2 signal elements. You are using 2 signal elements to transfer 1 bit. So that's why R is still a small r. Any questions? Now I'm going to move to next one, bipolar. Okay. So here's the idea of bipolar is somehow interesting. First of all, as you see here, I'm not gonna inside here in every bit duration, we're not gonna go to 0 or we're not gonna make any transition. Okay, this is different from what we did here. In every bit duration, there is a transition. In every bit duration, we have to go to 0 for synchronization. Okay, but for synchronization, we're gonna do something else. Because in every bit duration, if you go to 0 or every bit duration, if you make a transition, the cost, you are gonna pay a heavy cost. Okay, the cost is R actually was 2, and then the bandwidth, I'm gonna need double the bandwidth. This is the problem I had before. So here I decided in every bit duration, I'm not gonna use 2 signal elements to transfer 1 bit anymore. Okay, that's what we did here. Okay, so what we did here is somehow very interesting. So looks how this one works. Okay, let's start with the easy case. The easy case is 0. Every time there is a 0, it is 0 volt. Very easy. It cannot be easier than that. Okay, so every time 0, the bit is 0, 0 volt, 0, 0 volt, 0 volt. Very easy, right? Look at the 1. The 1. The 1 is gonna be every time there is a 1. The signal should be either positive or negative, not 0, right? So always for 1, it is positive or negative. Okay, but actually it's gonna be the opposite of the last non-zero voltage. For example, here we have 1. The last one was positive, so you have to go back. You have to go back to find the last one. The last one was positive, so this one will be negative. So in the future, if we have 1 more, if we have here 1 in the future, because the last one was negative, it's going to be positive. Is that okay? Is that a good idea to have positive, negative, positive, negative, positive, negative? Is that a good idea? For sure, this is a good idea. The bad idea is to have all the time positive, all the time negative. We did this inversion, okay? Number 1, to introduce transition. Number 2, for DC component, because negative, positive, DC component. Is that okay? So what is good about this one here, if you see, let me, yeah. If you have a pattern of 0, 0, 0, 0, 0, so actually it's going to be 0, 0 volt all the time. This is good or bad? For sure, that's bad. Okay, that's bad, because if you have 0, 0, 0, it's bad for synchronization. However, if you have 1, 1, 1, 1, so what's going to happen in case of 1, 1, 1, it's going to happen is that, assuming the beginning we are positive, so we're going to become negative, positive, negative. So everyone is going to make inversion. Everyone is going to flip. Is this good or bad? This is perfect. This is perfect. This is very good for synchronization. It's very good for DC component and so on. So we're going to solve the problem only 50% of the time when we have ones, but not 100% because of the 0 C. Okay. Any questions? We have another version. It's exactly the same thing, but we call it pseudo ternary. Okay, it's exactly the same thing, but the only difference is that we're gonna just change it. Here, every time you have 0, I'm gonna make 0 volt. It's exactly the same thing, but actually here, what we do, 0 here is gonna do, and the 1 is gonna make inversions. That's what we do here. 1 is making inversion, 0 volt. Here we're gonna do the opposite. 1 is gonna be 0 volt. Always, if there is a 1, 0 volt. And 0 is going to make inversion. You got what I'm saying? So exactly everything, but here 1 make inversion, here 0 make inversion. Here 0 is going to be 0 volt, here 1 is going to be 0. You know what I'm saying? So it's exactly the same thing. Any questions? Okay. Now I'm going to move to the next one. Next one, multi-level. Always we are looking for high bit rate. We agree on that. Always we are looking for high bit rate. Okay. One of the ways to have high bit rate is by having multi-levels. Okay, and even if you go back, Nyquist, in Nyquist we have log to L. Okay, that means if you need high bit rate, one of the things you have to increase is the number of levels you have. Okay, for example, as you see here, we're going to use 4 levels here. As you see, we can use 4 levels. In every level, I'm going to transmit 2 bits. Very interesting. So it's like two persons are gonna be transferred using 1 car. You got what I'm saying? So this is interesting. By this way, we can increase R. And as I told you before, if you increase R, that's good. When you increase R, actually, I'm going to reduce the bandwidth. I'm going to reduce the bandwidth needed from the network, which is good. And also, and this was a question in the quiz, I told you, what is the drawback of this? What's the problem of this one? Because if we don't have a problem, this would be a miracle. Miracle. I can have infinity bit rate. I can have infinity L, and then I'm going to have infinity bit rate. For sure. What was the problem of this one? Why I can just keep increasing L all the time? Yes, because the receiver is going to be more difficult, more complicated for the receiver to differentiate between the different levels. Okay, that's why we have limitation on L, unfortunately, for sure. Okay? So anyway, so this is, as you see, another example here. For example, in every time slot, I'm going to transfer 8 bits here. Okay, so anyway, so here I'm going to explain. We have different types of encoders here. So again, we agree multi-level is good because I can actually increase R. I can increase R. I can reduce the bandwidth. That's good. But for sure, I can't increase level too much. But here we have different types of encoders here. Every encoder, I'm gonna represent it using four letters this way. Okay. So I'm gonna explain when you see something like that what it means. Okay. So so here actually, the first 2 letters here are actually for the binary pattern. So these ones are actually describing the binary pattern. And the other 2 here are actually describing the segment element pattern. We have 2 patterns here, by the way. Maybe it's not obvious here, but it's going to be clear here. We have binary pattern. We have signal element pattern. So this is signal element pattern, like negative, 0, negative, 0, positive, positive. This is the pattern, right? Okay. So again, the first 2 bits are describing this is a binary. The other 2 bits are describing the signal element pattern. Okay. So let's see what these numbers mean. By the way, the first one here, we call it M. This one, we call it N. But anyway, let's see. So here, actually, when you see 8B in this example, what 8-bit mean? 8, the first part here. That means the binary pattern is 8 bits. And always we're going to use B binary because we always transfer binary data. So always we use B. We have to use B. And the number here is going to tell you how many binary number you are transferring. Okay, in every time slot. So here we are transferring 8. That's why you can see it's 8. Here, in this case, we are transferring 2. That's why you can see it. Any questions? Easy, right? Let's look at the second part. The second part here. The second part here, 6T. So what this one is telling me? 6 means we have 6 in every time slot. Okay, we have 6 signal elements. So you see here we have number 1 signal element, signal element, signal element, signal element, signal element, signal element. So we have 6. So this number here is going to tell you how many signal elements you have here in every time slot. Is that okay? What about T? T actually means 3, and this T should tell you how many levels you have. So here we have 3 levels. So here for the last one, we're not going to use numbers, but we're going to use letters. And when you are using letters, as you see here, if you use P, that means L is 2 levels. If you use T, that means L is 3. If you use Q, it means L is 4. You got what I'm saying? So for example, here, this one was 1Q. 1 means we are going to use only one signal element. Q means we have 4 levels. Q means 4 levels. Any questions? That okay? Any questions? Okay. So again, the way we write this encoder is actually N. For example, N, and then it has to be B. We use B all the time. And then we have M. And then after that, you are going to use a letter. This letter is going to tell you how many levels we have. So it can be T for 3, it can be B for 2, it can be Q for 4. Okay. Okay. Look here, very important thing. For the binary numbers, as you know, if you have, so this one is going to tell you, this one, as I told you, how many bits, n bits. We're gonna, every time we're gonna, our pattern is n bits, right? So how many patterns we have in binary? So in binary numbers, how many patterns we have? It's going to be 2 to the power of n. That you know that, okay? So here, this all the pattern we have, 2 to the power n. 0, 0, 1, 0, 0, all options, all different options, 2 to the power n. Is that okay? Okay, let's look at this part here. How many signal element pattern we have? What do you mean by signal element pattern? As you see here, positive, positive, negative, negative. This is a pattern, okay? So we can have different combinations with this pattern, like negative, positive, negative, positive, positive, negative. Sorry, 0. Okay, so we can have different combination. How many combinations of this pattern we can have? How many combinations? So actually, this is all the combinations we have for the pattern. So it's going to be actually L raised to the power M. L means how many levels we have. How many levels we have raised to the power M. Is that okay? So for example, let's look at this example here. Okay, so for example, in this case, okay, so here we have how many patterns we have. So it's going to be 2 to the power 2, which is 4. And yeah, and this is the 4 here. We have 4 binary pattern. That's okay. How many signal element pattern you have? You told me L to the power of M. L in this case is 4. We have 4 different levels or voltage levels. I'm going to raise it to M. M here is 1. Which is 4. That's what we have. So that's one of that. So here it can be positive 1. This is 1 pattern, a positive 3, because we have only, in every time we have only, I have to pick only 1, right? So it's going to be 1, positive 3, positive 1, negative 1, and negative 3. Is that okay? So it's only 4 ones. Okay. What about here? For example, if you have 8B 16. So in this case, 2 to the power M. So how many binary pattern we have? It's going to be 2 to the power 8, right? Which is 256. That's okay. How many signal pattern we have? So it's going to be T means 3. We have 3 raised to the power of 6. You understand what I'm saying? So that's all 3 to the power 6. Is that okay? No, because letter T here means, yeah, because 3 levels. So always the number of pattern is actually number of levels raised to M. This is M. M is here. Okay. T means 3 levels. The letter you are going to use at the end is going to tell you if it's 2 or 3 or 4. Okay. T is for 3. Is that okay? No, I'm going to take your question, but let me finalize my point here. Okay. What I'm saying easily is what I'm saying. We have binary pattern here, and we have signal element pattern here. Is that okay? Again, can you see again what do you mean by binary pattern? Yeah, this is the binary pattern here, right? What do you mean by signal pattern? Yeah, this is a signal pattern here. Is that okay? That's okay. So let me finish my point before I take your question, okay? So what's going to happen here, every pattern here should be associated with one level here. I'm going to distribute, right? This pattern this pattern here is going to take this pattern here. This pattern in binary is going to take this pattern in signal element, and so on. Is that okay? My question is, so at least this have to be equal, right? Or this one has to be greater, because every binary pattern I'm gonna give every binary pattern, I'm gonna give it a one signal element pattern, right? So I should have enough number of signal element pattern to give to the binary pattern. Is that, you understand what I'm saying? For example, I'm gonna say 0, 0, you are gonna take this one. 1, 1, you are gonna take this one, and so on. So you should have enough number. Otherwise, if this is not the case, some binary numbers I can't transmit them because they don't have a signal element pattern. So what I'm saying, at least you should equal, or it can be less. You know what I mean by less? It means I can have more signal element patterns than the binary data I have. Is that okay? And this is actually the case here. So the case here we have actually, if you use the calculator, you will see 2 to the power 8 is actually less than 3 to the power 6. So in this scenario, I have more signal pattern like this ones, more than the binary. Is that okay? Is that a good thing or bad thing? Is it something good or bad? It's good. Why it is good? Because I can exclude the bad pattern. The patterns that are creating problem for synchronization, the patterns that are creating problems for DC component and so on. Now I have the freedom. Now I have the choice, because I have too many patterns. I can see the wrong pattern. I'm not going to use them. You got what I'm saying? For example, one of the patterns actually should be positive, or negative. Such patterns, I'm not going to use them. You got what I'm saying? So I'm going to tell you the conclusion. Conclusion: we have pattern. We have a set or a number of all possible cases for the binary number pattern. Also, same thing for signal element pattern. It's good that we have more pattern in case of signal element, because we can actually we may not use all of them. I can exclude the bad ones. The bad ones. What do you mean by the bad ones? For sure, the bad ones, you already know from what I explained before. The bad ones, if you have like too many positive or too many negative, okay? Actually here, because I have too many pattern here in this exact scenario, because I have too many patterns, what I can do, I can use the patterns that have weight of 0, or I can use the patterns that have weight of 1. What do you mean by weight of 0? How can you calculate this weight? I'm going to tell you. Weight of 0, it means 0 means number of negative equal to the number of positive. So 1 negative, 1 positive, 1 positive. So 0 means the positive equal to negative, right? 1 means I have 1 positive more than the negative. Okay, so here you see negative. How many negatives you have? You have 2 negative. How many positive you have? 1, 2, 3. So that means I have 1. So I can do that for all the binary number. Either I can have weight of 0. That means there is a balance between positive and negative, or I can decide that, because for sure I don't have enough pattern for this one. I don't have. If I have enough pattern, this is a very good one. Okay, for this component, because the number of positive equal to the number of negative. So this is a very good pattern. That for sure I can't only use this one because I don't have enough for this one. Okay, to cover all the pattern we have. Okay, but this one is still okay because it's still the one positive more, so still balanced. Okay. Anyway, so what was your question? I answered it. Yeah? Okay. No, we always have 0 or positive 1. We don't have negative 1. So that's what we do here. So I have enough pattern. I decide. This is my choice. That's what I decide. So here I have 3 to the power 6 patterns. So I have too many patterns. Out of the, by the way, 3. I think there's a mistake here. This one you can do the calculation, but this one is actually, I think 700 something. Anyway, 3 to the power 6. You can calculate it. Okay. So because all what I need only 256 out of 700 something. So I'm gonna select only the good patterns. And in this case, I selected the patterns that have weight of 0 or weight of 1. What do you mean by weight of 0? Number of positive, here, 2 positive, 2 negative. Number of positive equal number of negative. What do you mean weight of 1? So I'm going to have 1 positive more, because if you see here, you have here, look, negative, positive, negative, positive, positive. So I have 1 positive more. So either all the pattern I have, either this one or this one. I decided not to do that. The pattern I selected, okay, I selected the pattern that give me this one or this one. Nothing else. This is the pattern I selected. I can select the pattern that can give me, because this is good for the transmission. You got what I'm saying? I can say I'm going to use weight 0 and weight -1, for example. I can decide that, but I'm explaining what usually we do here. Either we select this one and this one. Yeah. Anyway, let's come back to here. So here, so as you see here, first of all, try to forget this one for now. So how? Let's start with a simple one. 2B1Q. How 2B1Q is working? Okay, very simple. I told you every binary here has a pattern, has a signal pattern. Okay, and because here the pattern is just has only one signal voltage. So here I'm gonna say 0 0 is +1, 0 1 is actually +3, and so on. So I'm gonna use this pattern. So every time you find 0 0, I'm gonna put -1, +1. Every time I have this one, I'm gonna use this one. Every time I use this one. This is a very simple way to do it. It's a very simple way to do it. Every time you have a pattern, I'm gonna use it with a voltage pattern. Very simple way to do it. Is that a good way? Okay, for sure we agree that this is good for the bandwidth for sure, because you are using multi-level, but it's bad for everything else. So the way I did it here is bad for everything else, because if you have 0 0 0 0 0 0, so it's going to be +1 all the time. For sure that's not good, right? So if any one of this pattern is repeated, the voltage will be constant, which is bad thing. You understand what I'm saying? That is why we're going to do, this is a simple way to do it. It's a simple way. The simple way, I'm going to give 1 voltage for every pattern and use it. You got what I'm saying? But for sure, that's bad, right? So now I'm going to improve it. So now I'm going to do something better, but it's going to, for sure, it's going to be better, but it's going to be more complicated. So here, what I did, we're going to have this part here. Okay. So here, what we are going to do here is, look what I did here. In case of 0 0, okay, so 0 0 can be +1 or it can be -1. It's not only 1 voltage. It can be this one or this one. How I can tell? You can tell from the previous level. If the previous level was positive, so I'm going to select the positive. I'm going to keep it positive. If the previous one was negative, I'm going to keep the negative. Okay, but in case, same thing here, in case of 0 1 0 1, it can be +3 or -3, depends on the previous one. If the previous one was positive, so I'm gonna still positive. If the previous one negative, I'm gonna keep it negative. You see what I did? So here, that's what I did here. I'm gonna change. I'm gonna keep the same polarity. If the previous one is positive, I'm going to keep it +1. If the previous one is negative, so I'm going to keep it -1. If the previous one here positive, +3 or -3. Is that okay? This is not good. I'm going to tell you why. But this is a very interesting thing is here. Let's see what is interesting here. Okay. What's interesting here is in case of these two patterns, in case of 1 0, let me. Yeah, this one here are really more important. So see what happened here. Number 1, if it is 1 0, if the last one is positive, make a transition and change it to negative. If the last one was negative, make a transition to make it positive. So these two are going to make transitions. Positive, make it negative. Positive. But these two are going to keep the polarity. Okay. So that's why if you see here, So the first two here are gonna keep the polarity, the first two. Okay. So that's why, for example, if you see here 0, 1, if you look at 0, 1 here, this one was negative. Okay, I'm gonna keep it negative. 0, 1. Okay. Okay. Also, but the other two here are gonna induce transition. For example, here, let me go back. Here, 1, 1, 1, 1 is gonna make a transition. Yeah, the last one was positive. You have to be negative. Transition. Is that okay? Same thing for 1, 0. So 1, 0 here. You are negative. You have to be positive. It's gonna make a transition. So if you have 1, 1, 1, 1, 1, 1, 1, 1, it's going to be very interesting. So if you have 1, 1, 1, and I'm going to start with positive, the next pattern here are going to make it a negative 3. And then positive 3, negative 3, positive 3. Is that a good thing or a bad thing? For sure, that's a good thing, right? So if the pattern is repeated, the voltage is not going to be fixed. Okay. So this is true for the last two cases, but not for these two cases. For these two cases, for example, if you have here, if you have 0, 0, if you have something like 0, 0, 0, 0, 0, and I start with positive, so I'm going to continue positive because these ones don't make a transition. They don't change the polarity. Or if I start by negative, so I'm going to continue negative. You got what I'm saying? So now here, again, what's interesting here? Number one, I can significantly reduce the bandwidth, okay, which is very, very important. However, for DC component synchronization, whatever, I can solve it only 50% of the time because it's okay because this one is going to make a transition, but these two are going to keep the polarity. That's why for these two, we still have DC component problem synchronization and so on. Is that clear? Any questions? Okay. So I'm going to come to here again. Here, as I told you, we did something. Okay. Here, I did two things are very interesting. Two things here, I did them very interesting. Okay. The first thing is because I have more signal pattern, then the binary pattern I need, I'm going to choose the good pattern. That's good. So this is going to help DC components. It's going to help me because I'm going to use the good pattern. Is that okay? This is the first thing I did. First good thing I did. So this is number one. And because I selected good pattern, I'm going to do something else now. But because I selected good pattern, what's going to happen? Every time you are going to have a weight of 0 or 1. 0 or positive 1. Okay? So always you have balance. This is complete balance between positive and negative. This is actually the positive is one more. Is that okay? I'm gonna enhance it more. I'm gonna look how I'm gonna enhance it more. What if I have a pattern with weight 1? So that means 1 positive more. And then the next one also weight of 1. You got what I'm saying? So this one has 1 positive more. Next one has 1 positive more. Now I started to be concerned. Why? Because now what I want to do, what is good for DC balance, for DC component and all of them, is balance. You got what I'm saying? Now the signal is the average is going to have positive more because this one has 1 positive more, this one has 1 positive more. So I'm going to do something interesting. If this happens, I'm going to do enhancement right now. What is the enhancement? If I find two consecutive signal, the weight of this one is 1. The weight of this one is 1. What I'm going to do is, okay, why this is bad? This is bad because you have here 1 positive more, 1 positive more. So positive starting to become dominating, right? So I want to make a balance, right? So what we're going to do, I'm going to invert this signal and to transmit it. When you invert it, actually the weight is going to be negative 1. Now we have positive 1 and negative 1. So both of them are going to be 0 again. You got what I'm saying? So again, if it happens that one pattern has positive 1 weight one positive mode, next one has one positive mode, so I'm gonna flip this one. So flip means positive becomes negative, negative becomes positive. Flip it. When you flip it, so it's gonna be one negative mode. The previous one positive mode, they are gonna cancel each other and meet balance. Is that okay? Okay, but wait a second. How the receiver can know this signal is inverted? Otherwise, let me finish. Otherwise, if I use this pattern, I will find a different binary number because you inverted it. When you inverted it, it's going to be a different binary number. So the receiver, if receiver doesn't know this signal is inverted, so the receiver is going to come up with a different binary number communication phase. You got what I'm saying? So receiver has to know this one is inverted, so that the receiver has to invert it in order to get the correct binary number. Okay? So the question, how the receiver can know if this one is inverted or not? Very simple, very simple. Simply because the way I designed it is always I have 0 or 1. I will never get -1 unless it's inverted. You got what I'm saying? So for the receiver side, every time I receive a pattern like this one, I'm going to calculate the weight. If the weight is 0, it's okay, I'm done. Okay, I'm going to convert the signal to binary number, and that's I'm done. If it is +1, I'm okay, I'm done. But if it is negative means it's a signal because I'm not going to select any pattern that has -1. -1 can only happen if it's inverted. So before I go and to convert, before I convert it to a binary, no, I'm going to invert it first, then use the inverted one to get the binary. Yes, question. Still you have question or I answered it? Any questions? You understand here? So again, in conclusion, we did 2 enhancements here. Number 1, the redundancy in the number of signal element is going to help me to select a good pattern. This number 1. Number 2, I'm going to select here with 0, with 1, and then if it happens to have more 2 consecutive with 1, so I'm going to invert one of them. Any questions? Great. Okay, now I'm going to move to the next one. The next one is actually is used in Ethernet. Okay, keep in mind we always look for high bit rate. Okay, using the same because we have limited bandwidth. You should not ask for more bandwidth. Okay, so how can we maximize the bit rate using the same bandwidth I have? Okay, that's why this one is used in Ethernet. This one is called 4G PAM5. Okay, so let me tell you what this one means. Okay, 4G means 4-dimensional. And what is the meaning of 4-dimensional? It means I'm going to use 4 wires instead of 1 wire. I'm going to use 4 wires. So actually, everything I explained to before this one, this signal is transmitted through only 1 wire. So everything I explained, it was only 1 wire. 1 wire. So all the signal transmitted through 1 wire and so on. Is that okay? But for this one, because I wanna get very high bit rate. I wanna get 1 gigabit per second. Very high bit rate. Okay? So the traditional approaches are not gonna help me. I have to find a new approach. So here in the new approach, I'm gonna use 4 wires, as you see here. And the signal, as you see here, the signal has 4 levels. Okay, every level is going to be transmitted through 1 wire. So again, as you see here, so here 1 level, one signal element, signal element, and then I'm going to transmit all of them at once. Okay. So that's what we do in Ethernet. Okay. What is that? لا ما هو المفروض ان احنا يعني مش ساعات بتبص كده بتلاقي الوايرز مثلا ليها ديفرنت كلرز، واحد ريد واحد خلاص، ما هو من كده بقى لازم يعرف يعني دي حاجه مش يعني هو لما ادو كونكشن لازم بيبقى عارف ان ده هو الاولانيه دي الثانيه دي الثالثه ده الرابعه فاهم عشان كده في الوايرز بيبقى ليها different colors ماشي في الواير بنوز different colors here. Okay. So again, what's really interesting about this one, you can transmit 4 signal element at once, simultaneously at the same time. And the main motivation behind this is actually high bit rate. Okay. So if you do the calculations, let's do the calculation, and there is something interesting here. As I told you before, the bit rate, the signal element should equal C, right? N times 1 over R. Okay. C is constant. Most of the time, C is 1 over 2. Most of the time, it's constant. Okay. You should not worry about how this constant is calculated because in exams, in quizzes, I will give you this constant. Okay. But here, let's see what is R. R is actually how many bits we have here. This one is how many? Let me see. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 8 divided by 4. We have 4 signal element here, right? 1, 2, 3, 4, which is 2. So R is 2. Okay, R is 2. What's interesting here is actually C, because of the way we did it, and because we're gonna use some error detection correction schemes, we found that this constant actually is gonna be 1 over 4 here in this case. So this constant actually we were able to reduce it because the way we translated the signal, and because of we were able to reduce significantly the errors. So it's going to be 1 over 4. So in total, it's going to be here n divided by 8. So here total n divided by 8, which is really great. Very, very good here. Okay. At the very end, I'm going to give you. You can see, yeah. This is a comparison between everything I explained. One of the things you should learn is the bandwidth and bit rate, relation between bandwidth and bit rate. You can see we don't have too many. So for example, here, most of them n divided by 2. N divided by 2, this is the maximum you can get in 2 levels. In case of 2 levels, the maximum you can get is n divided by 2. Here also n divided by 2, but here for sure multi-level is a different way. So here, okay, let me. So this part is actually 2 levels. So the maximum you can get here is actually n divided by 2. This is the maximum. So here we're gonna get either n or n divided by 2. Okay, but here in multi-level is gonna be more for sure. You can see here, for example, here we have this is the best for sure, n divided by 8, right? So I can do the transition using n divided by 8. Okay, so n divided by 8 means it's 4 times this one, 4 times, right? Yeah. Or is it 4 or yeah, 4 times? Oh, sorry, this one is actually 4 times of this one. So here, this one needs 4 times the bandwidth. Anyway, so the last one I'm going to explain here, we call it multi-transition. The last one I'm going to explain. So here in multi-transition, you can tell from the name, if you want to know if the bit is 1 or 0, so it's not from the voltage level. It is from the transition. So the transition should tell you if it is 1 or 0. Okay, that's what I'm going to explain right now. So here in multi-transition, I'm going to explain this scheme, MLT3. So in this scheme, it works this way. I'm going to make it very simple. Look here. If the next bit is 0, so if the next bit there is no transition. 0 is not going to make transition. Okay, for example, okay. So if it is, if it's already positive and now it is 0, so I'm going to keep it positive. If it is negative, okay, I'm gonna keep it negative, and so on. There is no, so here, if the next bit is 0, there is no transition. Okay, and this you can see it here. Look here at this one here. Yeah, because this one is positive and this one is 0, I'm gonna keep it positive. Okay, look at this one. Okay, this is negative, and because it's 0, keep it negative. Is that okay? That's good. But so the 0 is going to keep the voltage, whatever it is positive, it's going to keep it positive. If it's negative, I'm going to keep it negative. Okay. But let's look at the 1 here. What the 1 is going to do? The 1 is going to make transition anyway. So the 1 will make transition. Okay. But so 0, no transition. So 0, you see here, no transition for 0. Zero here also no transition, right? It's going to keep the voltage positive, it's going to keep it positive, negative is going to keep it negative. One is going to make a transition, okay? But actually, here I have two rules here, because this transition, when I do transition, it can go to zero, okay, or it can transition to positive or transition to negative. One, I'm going to make a transition anyway, okay? But this transition can be to zero, can transition to zero, or positive or negative. How I can know if this is to zero or positive or negative? How I can know? Okay, you can know if, look at the rule here. If the current level is not zero, so I'm going to go to zero. So if the current voltage is not zero, positive or negative, so I'm going to go to zero, right? So transition is going to be to zero. But if the current level is zero, so the transition is going to be opposite to the last non-zero level. Oh, okay. Let's see the example here. You'll understand it. So let's look at this example. Look here. Let's start, for example, here with this one here. Okay. With this one. Oh no, let's start with, because this one is missing some information. So let's start with this one. With this one here. Okay. So for this one here, okay, because there is a, you can see I made a transition. Is that okay? Because this is zero and this one, so there is a transition. But this transition can go to zero, okay, or it can go to negative, can be zero or negative. So why I selected zero? Simply because that's what I told you here. Why I told you here? Because this one, the previous one, is not zero, positive or negative, and will go to zero. That's exactly what happened here. This one is positive, so the transition is going to be to zero. If it is negative, the transition also would be to zero. Is that okay? Now, if this one is one, if it is zero, now if this one is zero, okay? If you make a transition from zero, you are going to go to positive or negative. Which one? Okay, the opposite of the last one. So that's what I'm look here. So here I'm gonna make a transition from zero. But the last one, I have to go back until I find the last non-zero. The last one was positive, so I'm gonna go to negative. Okay. Let's see, for example, this one as well. Okay, here. Again, very simple. Because the last one is not zero, positive or negative, so I'm gonna go to zero. That's why the transition was to zero here. But look at this one. Okay, because the last one was zero, so the transition here is going to be the opposite to the last non-zero, which is this one. Anyway, think about it. I'm going to continue it next time, but let's use let's do the attendance quickly. Three, 7, 8, 6. What is that? Yeah. Again, this is, I was told, this is not my